Hey guys, welcome to week number 3 of the Ace Your IB Math Exams in 10 Weeks series. We're going through every possible topic, every possible type of question that might show up in your upcoming IB Math exam down the line in May 2026 this year, where each week we tackle 5 questions from all 5 different topics of the IB Math curriculum: number and algebra, functions, trig, probability and statistics, and lastly calculus. All of these questions, they are challenging, they're all fun to do, they're going to give you a sense of what the IB Math exam will look like. They're novel, they're new, you're not going to find them anywhere, so it's a very good resource to better prepare yourself for the upcoming IB Math exam. If you missed one of these weeks, one of these lists, you can find them in the description of this video, and do share them. Share the link for the YouTube videos and also the PDFs with your colleagues so you guys can study together. So without further ado, let's start week number 3 of the Ace Your IB Math exams in 10 weeks. All right, so let's start out strong. Start out with a deduction proof. We have to prove by deduction that the sum of cubes of 3 consecutive natural numbers is divisible by 3. Now, you can call these numbers x, x plus 1, x plus 2, or maybe x minus 1, x, and x plus 1. Anything that you prefer. All of these 2 options, they're going to work out. And you can even be more creative and call them something else, which are consecutive. It's going to work out as well. Now, I'm just going to call my integers x, x plus 1, and x plus 2. And we can say that because we're assuming x to be an integer, therefore the sum of these numbers cubed is equal to, and right now you can use Pascal's triangle to expand these binomials. So we have 1, 3, 3, 1, multiplying x cubed, x squared, x, and x to the 0, and then 1 to the 0, which is 1, 1 to the first power, which is also 1, so every one of these are going to be 1, which gives us x cubed plus 3x squared plus 3x plus 1. And then again, for this binomial right here, 1, 3, 3, 1, x cubed, x squared, x, and x to the 0, and then 2 cubed, 2 squared, now going from right to left, 2 to the first power, and then 2 to the 0. If you don't know how to do this, you should work on binomial expansions. We have a few exercises on binomial expansions coming up. So this can be rewritten as x cubed plus 6x squared plus 12x plus 8. Therefore, when we add these, we get 3x cubed plus 9x squared plus 15x plus 9, which is divisible by 3. And the way you're going to show the examiner that is by factoring out a 3 from these terms. So 3 times x cubed plus 3x squared plus 5x plus 3. You can leave it like this, or you can finish writing which is divisible by 3. Now, hence or otherwise, we need to prove by deduction that the sum of cubes of 3 consecutive natural numbers, which are these, it is also divisible by 9. So first of all, what does it mean to be divisible by 9? It means that it's divisible by 3 and then by 3 again. We already know that this is divisible by 3. Therefore, if we can prove that this is also divisible by 3, that means that we could factor out a 3 from here, which would represent, in the end, a number which is divisible by 9. Now, how do we do that? So proving that x cubed plus 3x squared plus 5x plus 3 is divisible by 3, which means that 3 times that is divisible by 9. Now let's say that x itself is a multiple of 3, meaning that it can be represented by 3 times some integer, so 3 times k. So we're assuming that k is an integer as well. Do notice that any number that can be written as 3 times an integer is a multiple of 3. Now, if x is a multiple of 3, what we're going to have for this green box is 3k cubed plus 3 times 3k squared plus 5 times 3k plus 3, which is 27k cubed plus 27k squared plus 15k plus 3. Which is indeed a multiple of 3, as we can see over here. So there we go. Now, what are the other possibilities? The other possibilities are, when we try to divide a number by 3, we get 1 as the remainder, which means that the number is not itself divisible by 3. It leaves a remainder of 1. how can we represent such number? We can represent it as 3 times k plus 1. If you try to replace k by any integer, let's say 2, we get, in this case, 7, which when dividing by 3 gives us 2 plus 1 over 3. So the remainder is 1. Now, if we make that substitution, we get 27k cubed plus 54k squared plus 42k plus 12 after simplifying everything, of course. And this is divisible by 3. So is divisible, or it is a multiple of 3. Now lastly, if you assume your x to be 3k plus 2, which means that it's a number that when divided by 3 gives us 2 as the remainder, what you get is 3 times 9k cubed plus 27k squared plus 29k plus 11, which is also divisible or a multiple of 3. And this means that in any case we will get a multiple of 3 for this green box, which means that 3 times that will be a multiple of 9, meaning that it's divisible by 9. In this exercise number 2, we have a nice little mix between a logs and between trigonometric functions. And converting this log to an exponential, which means going from the right to the left hand side over here, we get sine of x to the power of 1 over 2, which is root of sine of x, equals cosine of x. If we square both sides, we get a sine of x, which is equal to cos squared of x. And by replacing this cosine squared of x by 1 minus sine squared of x, we get a quadratic equation in which we can use the quadratic formula to solve. Now that comes from the fact that we can replace sine of x by y, solve it for y, and then substitute sine of x back into y. So we have sine squared of x, which can be represented by y squared, plus y minus 1, which is equal to 0. Now y is, using the quadratic formula, negative b plus and minus the root of b squared minus 4 times a times c over 2 times a, which means negative 1 plus and minus the root of 5 over 2. Do notice that both the base and what shows up inside the log, they have to be greater than 0, meaning that the only possibility here is to have negative 1 plus root of 5 over 2 as our y, which means that sine of x is negative 1 plus root 5 over 2. So consequently, our sine of x, which has to be positive, is negative 1 plus root of 5 over 2. Alright, so on to exercise number 3. An IB student admires the city view standing on top of a building. Wow, that sounds dangerous. He notices a taller building next to his. So given this construction, it's probably a good idea to go ahead and mark this horizontal line, one which gives us, of course, 2 straight angles. The angle of elevation of A from B is 25 degrees. So from B to A, we have 25 degrees. And the angle of depression from the top of the taller building C to the top of the shorter one is 18 degrees. Now, what is, or where is this 18-degree angle? It helps also to build this horizontal line so we can see this 18-degree depression angle. Now, if this is 18, then this alternate interior angles, this is 18 degrees as well. And if this is 25, this is 25 as well. Knowing that the height of the taller building is 130, which means that this is 130, we need to find the height of the shorter one, which we can call x, and x can be found over here as well. Now, if this is x, this guy right here is 130 minus x. And given that the adjacent side to these two angles, the purple one and the orange one, they're the same, a good idea is to use it with the opposite sides using some sort of trig function, which in this case is, of course, tangent, opposite over adjacent. So we have the tangent of 18 degrees equal to 130 minus x over that adjacent side, which we're going to call d. And we also know that tangent of 25 is x, which is the opposite side, over d. Now, if you rewrite d as x over tangent of 25 degrees, we can replace it over here and use this equation to find x. So 130 minus x over x over 1025. Now we can cross multiply the x over 1025, which gives us 1018 times x over 1025 equal to 130 minus x. Now you can definitely manipulate this equation in order to find the solution, or you can just throw this into your GDC in the numeric solver app, which will give you x approximately equal to 76.6 meters. And don't forget, of course, to change your setting from radians to degrees if it is in radians right now. On exercise number 4, we have a probability question, one that involves conditional probability, the given that types of exercises in probability. And we notice the given that because of this notation. In this case, P of B given not A and P of A given B. And the best approach for this exercise here is to use both the formula for the conditional probability, but also a Venn diagram whenever we get a chance to use it. We know that P of A given B is P of A and B over P of B. So this formula is in the formula booklet, which means that this 0.5 represents the probability of B and not A over the probability of not A. And the 3 over 11 represents the probability of A and B over the probability of B. Now, a little harder to spot, however, given that the probability of A is 0.2, we know for a fact that the probability of not A, which is the complement of A, is 1 minus 0.2. So in this case, 0.8. Now notice that we can use it here and find our probability of B and not A as 0.5 times 0.8, also known as 0.4. And if we call the probability of A and B x, we can represent through a Venn diagram P of A and B over here, P of B and not A over here. Also, knowing that P of A is 0.2, this probability is 0.2, therefore this is 0.2 minus x, x being the intersection between A and B, and P of B, which can be seen here, is equal to 0.4 plus x. Now we have everything that we need to finish this equation, to finish solving this equation. So we have 3 over 11 equal to x over 0.4 plus x. If you cross multiply, you get 1.2 plus 3x equals 11x, which means that 8x is equal to 1.2. Therefore, x, which is the probability of A and B, it is equal to 0.15. And we're not done just yet. We need to find P of B given A, which is probability of B and A, which, by the way, is the same as the probability of A and B, over the probability of A, which is 0.2. Now, probability of A and B is 0.15, so we get 0.15 over 0.2, also known as 0.75. And there you have it, exercise number 4. All right, last exercise of the day. This is one that looks very simple for those who are not paying attention, because this is actually not the graph of the function, but of the derivative. So you need to be extra careful with this exercise. A function f is defined between a and k. Now, this is not f, this is actually f prime. The graph of its derivative is given below, f prime. Find all values of x where the graph of f is increasing. Now, what makes a function be increasing? A function is increasing in an interval where f prime is greater than 0, meaning that in this case, given that we have in front of us already the function f prime, or the graph of the function f prime, we need to look for intervals where f prime is above the x-axis, meaning it is positive. And that is between a and b, not including a and not including b, between the origin and e, not including either of those as well, and from e to k. How can you write that? Well, from a to b, from 0 to e, and from e to k. Now, another trick question. Find the value of x where the graph has a local minimum. What does it mean to have a local minimum? It means that the derivative is equal to 0, the derivative of the original function, and f prime goes from negative to positive. Why is that the case? Well, let's just picture a function which has a minimum right here. The derivative is negative, then it's 0 at the critical point, and then it becomes positive. which in this case, given that the derivative is negative over here, and it goes from negative to positive at the origin, then the local minimum is at x equals 0. And that's what you write in the exam. F prime of x is 0 at the origin, and it goes from negative to positive. That's it. Now, what about point of inflection? That's when the second derivative is equal to 0, which can be found by finding the slopes of the first derivative. What do I mean by that? If this is already the graph of the first derivative, the second derivative is equal to 0 at the minimum and maximum points, because these are the points where the derivative of the derivative is equal to 0. Now also the second derivative needs to change either from negative to positive or from positive to negative for it to be considered an inflection point, which is easy to verify because, for example, here to the left we have negative slopes and then over here positive ones, which means that the second derivative goes from negative to positive, then over here from positive to negative, and then negative to positive again. So all 3 points, x equals c, x equals d, and x equals e, these are all inflection points. So how do you justify that? Well, in all of these 3 points, the second derivative is equal to 0, which can be verified because these are the maxes and mins of this function. And also the second derivative changes sign from negative to positive or from positive to negative. Now the last and hardest exercise, the area enclosed by the graph of f prime, and the x-axis was given. It is equal to 25. Given this, whatever this is, we're going to use it later, find the value of f of 0. Now, if we're thinking areas, we're thinking integration. If and only if that region is above the x-axis, because if it's not, we need to adjust the sign. What that means is this area, for example, is equal to the integral from a to b of the function, which, by the way, is f prime, not f. However, this area right here, given that the integral will give us the negative area, we need to adjust it, we need to fix it by placing a negative sign in front of it. So this area is represented by negative integral from b to 0 of f prime of x dx. And when you add all of those, you should get 25. So we have the integral from a to b of f prime of x dx minus the integral from b to 0 plus from 0 to e plus the integral from e to k of f prime of x dx equal to 25. Now, if we integrate the derivative, we go back to the function. And if we have an upper and a lower bounds, we just need to replace the upper and the lower bounds in the function that we get, which in this case, it's the original one. It's f of x. What I mean by that is, in this first integral, we're going to get f of b minus f of a. Now this f is the original function, minus f of 0 minus f of b. And this sign, of course, is due to the fact that the area is below the x-axis, plus f of v minus f of 0, plus f of k minus f of e. And this is equal to 25. Now, there are a few things to simplify. We have 2f of b minus f of a minus 2f of 0 plus f of k equal to 25. And now we go back to the exercise and we can see that this was given 2f of b plus f of k minus f of a. This is equal to 35. So 35 minus 2f of 0, this is equal to 25, which means that f of 0, it is equal to 5. And that's it. That was week number 3. I'll see you next week in week number 4 of the ACE or IB math exams in 10 weeks. If you missed one of those, check the links in the description of this video. You're going to find the PDFs there. You're going to find the other videos there. And do share that with your colleagues so you guys can study together. I'll see you next week.